Okay, I think I kind of I slowed down a bit last time, so I think that's fine. I'll continue to go at whatever pace you let me go at. So I may not get through all the slides I prepared, but that is absolutely fine. I think I'm going to go back to where we got to last time. I think we were, if I remember correctly, I just showed you shallow handlers. And we have the operational semantics and the types of shallow handlers. But maybe I'll just recap that to remind you. What was nice about shallow handlers in particular is it meant that this concurrency example is more straightforward. We didn't have to do any funky mapping between resumptions and threads. Just to recap, the idea was we wanted to implement cooperative concurrency. We have this yield effect, and with shallow handlers, threads, and the resumptions we end up capturing have the same type, which means we have this very direct implementation that simply says when we yield, well, we stick the continuation on the end of our queue. Right. And then it will take the next one off the head. And we briefly saw the operational semantics for shallow handlers, which were just like the operational semantics for deep or parameterized handlers, with the key change being that when we capture this evaluation context in the resumption, we do not reinstall the handler here. Hence, if you look at the example back here, each time we perform an operation, we recursively call the function and it reinstalls the handler manually. Okay, and I showed the typing rules. The key aspect of these things, well, where we see that the handlers are shallow here is that the resumption is returning something of the input type to the handler. So if we want to handle the rest of it, we have to do that explicitly. Okay. So now I'm going to show you, I'm going to just keep on showing you more examples actually, but yeah, question.
I didn't follow you said, sorry. Before you said typing rule for shallow.
For what? To change it to deep handlers, we just change this to a D instead of a. So the handler is taking a computation that returns values of type A and performs effect E, and interpreting that as a computation of type D, where D is some other value type and effect type. If you were doing deep handlers, the only thing that would change there is that would be D. It would be in D, representing the fact that it has to be handled by the same handler, because that's the only way this is the only thing we have that allows us to turn one of these things into one of these things. I guess if I go all the way back to did I show the, why don't I just show you the semantics wherever it is. So here we go. This is parameterized, which is, but you could ignore the parameters. The key difference in the operational semantics is that you see that the handler appears in the body there. And then if we look at the types, we've got a D here instead of an A bang E. Okay. And then if we get to there we go. So I'm going to show you various other examples that will illustrate other features we have here. So with this cooperative concurrency example, it'd be kind of nice if we didn't just have a static collection of threads. We might want to be able to dynamically fork new ones. The first way I'm going to do that is with an operation. I'm calling it ufork because it's inspired by the Unix style fork. So I don't know. who put your hand up if you are familiar with fork in Unix? Yes, most people. Anyway, if you're not, then I mean it's a little bit of a weird way of doing threads. You basically create, when you perform fork, and that returns a process ID, and then the rest of your program actually gets run twice, once with the new process ID and once with the parent process ID. So then you write a conditional in your program to simulate the two different threads. And this is an abstraction of that where we just use a Boolean, because I can't remember which way around it is. I think true represents the parent and false the child. The nice thing about this is there's nothing higher order about it. We'll come on to a higher order version of fork, but things get a bit more complicated in one dimension there, because you then have to have operations that themselves take computations as arguments, and that's a bit messy. Particularly if you look at the algebraic account of these things. But this is still can be treated as an algebraic thing. So an example similar to the one we had before, and you can see the sort of ugliness of this Unix style thing. This is sort of simulating having a main thread, and I'm kind of denoting that by printing out M whenever we're in the main thread, and two child threads. Actually, is that right? Yes. No, that's right. Yeah. So I got it the wrong way around. ufork, if it returns true, then it goes into this branch. So the true branch is the child, and the false branch is supposed to be the main thread. So the else branch corresponds to carrying on running the main thread, and then it's going to fork off a new one, and so forth. Jan, you're looking very perturbed.
Yeah, or we're not.
Oh, you want this to be nicely lined up so that you can see that it's in different threads? Yeah, well, do that in your head. And
so, if one just one more line of the else protect thread, then you have the main thread.
Yeah, I don't know. Actually, I don't know why. I don't know why I did that. That is a good. Yeah, that's true. These are the child threads. This one, and then everything else is the main thread. I'm not quite sure what happened there. I will amend the slide. This is the most important thing I've learned this week. Format. Anyway, so I've defined this name for this collection of effects, parameterized by, we might have some other effects as well. And we can take, I've gone back to the parameterized version. Again, maybe I should have stuck with the shallow version, but of the concurrency handler we already had for yield. And we can just extend that with a case for fork. It's actually a little bit interesting here, because what we actually want to do, you'll see, we've got the resumption, and that's the thing that, remember, has this conditional in it. It's expecting a Boolean, and we're actually going to invoke it twice, once with false and once with true. And let's see. There's a choice of semantics here, of course. I guess this one is saying, well, we'll do the true one first, And remember, in this parameterized version, we're storing the queue of other resumptions as the parameter. So right, what's happening here? Yeah, when we do a fork, we're going to immediately run the child thread we've forked, and then we want to stick the parent thread onto the end of our list, and that's what's happening here. So what is that parent thread? It's a function that's going to take the list of other resumptions and invoke the continuation again, but with false. So yeah, we can relatively straightforwardly do this, but it is invoking the continuation twice, which is, if you think about what Unix does, that's exactly what Unix does.
So with that, sorry, so I would expect that the list of resumptions is stored by the handler.
Yeah, so the parameterized handlers take this is my type of a parameterized handler. It has a parameter that gets threaded through everything, and then this is the input computation type and the output computation type. And every time you invoke a resumption, you have to pass in the new value of the parameter and the return type of the operation that you're handling. So fork is returning a Boolean, so that's why we're passing in the true or a false here. Yield is unit to unit. So you see a unit being passed in here and here.
So when you are defining the effect,
Yeah. You're doing a Phil Wadler and turning up and saying, "Oh, give me the whole course again," having not been to the. But yes, I haven't. This is the thing that you wrote. You write initially. You write a program that has no meaning at all. It's just, or rather, yield and you fork. We haven't given them a meaning yet. And you then afterwards, and I haven't cooperate is defined as it was defined before on a slide you've never seen in terms of co-op, and that invokes the handler. It takes a collection of threads here as just the main thread, but now we're able to fork off new ones which we previously weren't able to do. Yes?
What is type for you then one?
Nope, it's a parameter. It's just this type actually. I'm just using it as, this is just a shorthand for that. So it meant cooperative concurrency with Unix style fork, parameterized by whatever other effects I might also want to perform here, because we might be doing some other things. Oh, there's a typo. Yeah, there's something weird going on there. No, it's not the order. Yes, you're right. It should say one bank OUE. No, of course. Oh, yeah, and another point here. Am I doing that? We can easily change the scheduling strategy here just by, well, there's various options here, but if we just flip the trues and falses around, then we get different behaviors. So what I was doing there, as I said, this is when you do the fork, it will run the child first, and it will stick the parent on the end of the queue, or the continuation of your current thread on the end of the queue. But if we flip those round, then it will do the opposite of that. So you see that by the interleaving we got there. you see the main thread happening sort of periodically, but when you fork off the child thread, it gets an opportunity to run. If we did it the other way around, then the main thread essentially runs to completion and then the other ones interleave. And this is one of the major attractions, actually, of handlers. I mean, I know I'm showing you this in a very sort of toy, esoteric situation, but the point is you can very easily customize this. You could just, at some particular point in your program, you know that you want to use some other scheduling strategy. You can easily do that at whatever granularity you like, just by installing a slightly different handler. Now I'm just going to show you a variation on this, which is probably more like what you might want to use in practice, but is the signature is more complicated because this version of fork takes a thunk. And the interesting point is that the thunk itself, if I fork off a thread, it may want to fork off other threads and yield and perform whatever my other effects are. So this is actually a recursive effect type that we're defining there. So, yeah, still not got my formatting quite to Jan's taste, I think, but I mean, this looks less disgusting because it doesn't have these conditionals everywhere. Doesn't, yeah, looks less like it's written in continuation parsing style. Yeah, maybe again I should have done a shallow version of this. So, if you recall, you maybe do not recall, we had co-op with is basically a function that turns a thread into a resumption. Is that right? Yes. But yeah, again, it's a relatively straightforward definition. And let's see, is this doing the same thing? Is it immediately running the child that you're forking off? It is, as in it's, yeah, we start running the new thread and we add the resumption onto the end. It is not a typo. No, this is the type of a parameterized handler. It takes a value, it takes a computation, and it gives you back a computation. I kind of write this for the type of normal deep handlers, and then if there's a parameter, so it's not a typo. It's a different kind of function. This one goes from computations to computations. The normal arrow goes from values to computations. This is actually a ternary operator. No, it's all right. Keep asking, even if I covered it before. Okay, and yes, if you run that, you get the same interleaving we saw for the first case, and we can do the same kind of thing. Well, if we want to change the scheduling strategy, we can. We just run the resumption immediately, and we stick the co-op with T onto the end, and you get a different result. So, any questions about this? Is this utterly confusing? Or yes? Of course, was, yeah. I have to go back quite a way, but yes, absolutely. There we go. So what's going on here? Well, we want to take something of this type and turn it into something of that type. So it must take a list of resumptions and then a unit, and we need to get out well, not something of that type, but something of this type that that has had all of its yields handled. And well, how do we do that? We handle it with the co-op handler. It's pretty much the only thing it could possibly be. And then yeah, cooperate was converting all of these threads into resumptions in order to pass into in order to work with co-op. Yep.
What about taking so that typing goes for the shallow?
Yes.
So I'm a bit confused how you get rid of the E.
How you get rid of the E? Where?
In this case, D would not have the effect of the handle.
D can be anything at all. So it could have the same effects. It could be some other effects. What really a handler here is doing is taking a computation over one effect signature, interpreting it as a computation over a different one.
So if I had a handler that would handle multiple times one effect, I would have a base case that gives the effect back.
So an example, do I have an example of that here? We might have an example that crops up later. But an example you might have, for instance, is supposing you have a standard way of handling some form of I/O or something, printing. And then you say, oh, well, I'd like to intercept that. So I want to log every time I print and do something else. I could write a handler that does that logging, and then, having done the logging, it just prints again. And then that print will get handled in the standard way when it bubbles up to wherever the standard handler for that thing is.
But I'm thinking like in the case when you try to implement deep handlers with shallow like the person starting yourself.
I'll get onto that. Right, yeah. If you want to implement deep handlers, using shallow handlers, that's straightforward because all you do is you define a recursive function. I've got slides on that. I can show you that later. But in fact, yeah, I forgot about that. I've got a load of examples, and then I've got some. I can maybe give you options as to what I show you, but I can explain how you go back and forth between the two later. So I've showed you the higher order fork example. Here's a more interesting example, which is pretty hard to do with deep handlers. In fact, what we're going to do here is we have two different computations we want to handle. So this is, well, sort of the Unix theme again. Unix pipes. Maybe put your hand up if you're familiar with Unix pipes. Most of you. So anyway, the idea is you have one process that's sending output and another one's receiving input, and you connect the two together. So we're modeling that kind of scenario by having a sender computation and a receiver computation. And the sender computation is just going to, occasionally it will output natural numbers and then return the unit. and the receiver is going to receive natural numbers. And the idea is we want them to synchronize, as with a Unix pipe. So here's a very silly, not particularly useful example of this. It's actually quite similar to the generator example I showed before. This is just a function that's just going to send a sequence of natural numbers, ever increasing sequence, and I'm going to just pipe that to another computation that is just going to receive one natural number and then return it. And this is how we can do this with shallow handlers. By defining two mutually recursive handlers. So we're relying on the property that the resumption is not automatically having a handler wrapped around its body. Let's see if I can work through what's going on here. We're going to start off with this function, which is going to take a producer and a consumer. Might have helped if I'd written some type signatures here, but I haven't, I'm afraid. The consumer is the one that's going to be doing receiving. If it finishes, then we just stop. We've got our value. We don't care if there's more stuff to be sent. If you come across a receive, then we need to work out how to get the value that was sent. So we're going to do that by invoking another handler, copipe, which takes the consumer and producer. But the consumer is just going to be the resumption of this computation. And all that happens is, well, we run the producer, and when we come across a send, we go back, coroutine back to the pipe function and pass in the value that was sent to the consumer. And the consumer was expecting a natural number, so that's what we pass in. So this will just kind of go backwards and forwards. I can show you a little example of how this pans out. If we try to do pipe of nats 0 with grab a nat, then what happens? Nats 0 is going to do a send. Oh no, sorry, I've got this the wrong way around. We start with the consumer. Grab a nat is just going to do the receive, gets to here. Its resumption is, there's nothing left to do. It's just the identity function. It will go over to here. You're running copipe with the identity function. That was its resumption. And nats of 0. That nats of 0 is going to do a send and then do nats of 1. And the send is handled here by invoking pipe. And the resumption is nats of 1 here. But then, yeah, we just get a value out, we return 0. So, yeah, fundamentally what's going on here is with deep handlers correspond to folds or catamorphisms over a data type. And that works absolutely fine if you want to handle everything uniformly all the way down. This is a different kind of recursion scheme we have here. So you could define a version of handlers that captures, they're called mutumorphisms, where you have a fold over or you could view this as moving into a different category. A fold over two mutually recursive things. With shallow handlers, rather than doing a fold, you're essentially just doing a pattern match on the data types you've got, and then you have to do all the recursion manually yourself. So if your recursion scheme that you're trying to implement is something more complicated, then it's easier to do with shallow handlers. Although there's another thing, yeah, in the Frank programming language, we can write this handler as like 3 lines of code, and using multi-handlers, which actually explicitly allow you to handle 2 computations at once. So it's even cleaner than this. But any questions about this? Yeah. Multi-handler can handle, yes, several computations at once. So a binary version would handle both of these at once. Yeah, I'll show you that in a minute. Yeah, encoding shallow using deep is more interesting. The intuition is it's very similar to the way in which you encode the predecessor function using a Church encoding. Yeah, this can be done using parameterized handlers, but that's annoying. All right, my next example, I'm going to show you something maybe a bit more practical, and this sort of kind of comes from the way in which Frank does things, where you treat your built-in effects in the same way as your user-defined effects, except they're magically handled by the system. So, and indeed, I think you actually have this console effect in Frank. So we have an input character operation and an output character operation, and we might define print as taking a string represented as a list of characters, and you just output them all. And then this is state generative in the sense that it's like ML style state, which is also, we're going to assume this is a built-in thing. And here actually you see this use of parameterized operations again, because yeah, if I create a new state cell, I can create one of any type I like. So new is called ref in ML. It takes a value of type A and it's going to give back a reference. And yeah, we're assuming references are also a built-in type here. We have a write operation that takes a reference and a new value to write to it, and a read operation that returns the value returned in that reference. So we're just assuming this as built-in stuff. And I'm going to use this to implement actors on top of the cooperative concurrency that we had. So what are actors? Or what's my idealized model of actors anyway? Actors, in this setting anyway, corresponds to, you can think of them as separate concurrent threads or processes, but every actor is addressable and has a mailbox. You can send messages to it. Yeah, actually, in Erlang they're called processes, I guess, which is why I've got process ID here. I think process is actually a lightweight thing, not like a Unix process. And a process ID is just going to be, I'm just modeling that as using shared state as a reference to a list of messages. This represents the mailbox. And the signature for an actor, I'm assuming the messages all have the same type. So an actor whose messages have type A has these 4 operations. Self gives us back the process ID for the current actor. Spawn, it's a bit like fork, allows us to create a new actor with a mailbox type of an arbitrary type, B here, and you get back the process ID, which means you can then send messages to it, because send allows you to send a message to of type B to an actor that is expecting messages of type B, and you can, if you're an actor of type A, you can receive a message of type A. So here's an example, a classic example people write when they have actors. We're just going to spawn a whole load of processes and then send messages through the chain of processes. And I'm printing things out so that you can see what's happening. So this is spawning n processes, and each successive one is going to receive the message and then send it on to the next process. And then at the end, it just prints out. It sends the message. Ping. Yeah, to the final one. So if we want a chain of length n, we invoke this spawn many with the current. This is the process ID of the initial parent, and receive the message and then print it out. Yeah, okay. So anyway, the interesting part of this is going to be the handler. And this is a handler. It's not going to do everything, but it is going to take an actor computation. And here you see we're actually interpreting that as a computation that has other operations still to be interpreted. It's interpreted in terms of our existing cooperative concurrency effect, the one with higher order fork. And the effects we're parameterizing by includes the state effect. I think there's a mistake. Oh, no, that's true. I was going to say we also need the print. We need the console effect, but actually we don't, because here there's no printing going on. It's only when we instantiate it that we will see that. And you'll see in this handler, there are some operations being handled over here that are then implemented in terms of other operations. And maybe I should, why don't I go through what's going on here. So this is a parameterized handler. The parameter that's passed through is the current process ID of the computation being handled. And then it takes that computation and interprets it. So if we come across self, then, well, mine is my process ID. That remains unchanged, and we also need to return that to the resumption. If you want to spawn a new one, then we get a new reference, a new mailbox, and yours is the new process ID, and we fork that off using this other fork operation. But inside that, we re-invoke the same handler with yours. What was you? Oh, you is the new actor is you. So we just run that there. And in the resumption, where spawn is expected to return the process ID, so that the calling process can then send messages to it. Send reads a message. This is just reading the list, the mailbox for yours, and it just adds the message onto the end of its queue and writes it back into that reference. Receive is, I think, a bit more interesting. Do I even have the definition of? Oh no, I do. Right, yeah. So it's actually calling this receive when ready function, because the problem is if this is blocking, you can only receive a message if there is one. So it looks up to see if I have any messages. If I don't, then I don't want to block. I want to let the other computations continue. So we yield and just recurse. If there is a message, then we need to update the mailbox to consume the message and pass it into the resumption. These are the effects that that we can perform inside our threads. I can't remember what the definition of co was exactly. It does put it next to it, you see, but it also puts it inside the fork. So you are allowed to perform, you're allowed to access the references at this level, but also in your child processes, because it appears there. No, it's important that we put the whole thing in there, because if we did just that, then you'd only be able to use state in the main thread, and you wouldn't be able to use it in any of the child threads. Yeah. No, this doesn't. Sorry. No, it doesn't allow it to use. It doesn't allow it to use any of these constructs. It does allow it to use all of the ones in here. All of these. All we're doing here is we're interpreting all of these things in terms of cooperative concurrency and state, and then we can compose with other handlers, which will say how we want to handle those, and we could use different handlers to get different scheduling strategies or whatever. Yeah. This is a parameterized handler, which means it's always going to take a process ID of type A, and then whatever the return type of this operation is. So in the case of receive, it's going to be an A. So it takes a process ID of A and a message of type A. Yeah. That's parameterized handlers work that way, because you might, every time you continue, you might want to update the state, and we absolutely do here in some situations. For instance, when you do the send. No, sorry. Do we ever update it? We must do, surely. What am I missing? Oh yeah, it's true. Maybe we don't actually update it except by this recursive call to the handler here.
And you don't have the ball. It's not receiving it.
Right, but that's a different handler. So it's possible you don't actually need a parameterized handler here. And you could just treat this as a normal function. No, actually, thinking about it, it's not just possible, it's true. You never update your process ID. It always remains the same thing. So actually, you don't need a parameterized. It's overkill. Anyway, having defined that, we can then compose it with other things. So here we're composing it with this cooperate function, which had the co-op handler, and that tells it how to interpret all of these, the fork and yields that we had. And I'm assuming that read, write, and new are built-in effects. So it will actually print out things. But this is, yes, just another illustration of how you can compose these things together. Okay. Oh yeah, and you could. It's maybe instructive to do something like this. You could do a shallow handler version, or you could try and write. There's no reason why you couldn't write a version of this that does not go to this co-effect, but instead interprets all of these things directly. But then you have less flexibility. You can't plug in different implementations. Okay, where are we now? We had some questions about relationship between deep and shallow handlers. I think I'll spend the rest of this lecture talking about in a bit more detail about that. So these are how we characterize deep handlers. As I've said before, the key point in the typing rule is that the return type of the resumption is the same as the final return type, this D here. And in the operational semantics, you wrap the handler around the resumption. And as I just said, it's a folds that we're performing over the computation tree. The shallow handlers, these are the only things that have changed. The resumption is not returning D, it's returning A bang E instead, and we do not wrap the handler around the body, which means that we can insert whatever handler we like there. And this corresponds to doing a case split on the computation tree. So, I mean, if what you're actually doing is naturally expressed as a fold, it's a little bit more painful here because you have to explicitly invoke the recursion each time. But that's only a minor thing. Here's some examples. This was the handler for choice that always was true. And here you see it's slightly more annoying in the shallow case because we have to recursively invoke this function here, whereas in the deep case, that automatically gets done for us. And similarly, here's the version that invokes the resumption twice. You have to write this small amount of extra code. We can do a reader example. Similarly, you have to write a little bit of extra code there. A summary here. Deep handlers can be a bit more concise in the examples I showed you. And because you've got this uniformity, it turns out to be easier to implement efficiently. Shallow handlers, well, I showed you, we can do things like the pipe example. So if you're following a recursion scheme that isn't the standard one, they can be more convenient. And also, we can plug in different handlers at different stages. I guess I've not really shown an example of that other than, well, again, pipes. And parameterized handlers actually get you most of what you want most of the time there anyway.
Well, do language implementations tend to pick one or the other?
Yes. Well, that you do both. Language implementations tend to have started doing one and then realized that, oh, it might be convenient to offer the other as well. If you just do shallow, then you don't need to do much else. But I guess a whole load of the initial experimental implementations people did were deep, and then they kind of thought as an afterthought, oh, maybe we should have a way of supporting shallow handlers. So Coca does that, for instance. Lynx does that. Whereas Frank was always shallow and doesn't do anything special and had no aspiration to be fast anyway, so it wasn't really a consideration. Anyway, we can encode deep handlers as shallow handlers in the way I've shown you. This is a rather a more formal explanation of that. What am I doing here? Whenever you have a handler, you define a recursive function, and then you make sure that the resumption gets wrapped in a call to the recursive function that we thread through everything. It's just the obvious thing you would do. Shallow as deep is also entirely doable. I should point out, shallow handlers are also, they're pretty useless if you don't have some sort of recursion as well, because otherwise you just do one step. Whereas deep handlers build in a form of primitive recursion, so they're quite powerful on their own. No, it's a local transformation. Same in the other direction as well. Both of them are. Okay. You have to change the. You do have to change the body of your handler, but it's an entirely. Nothing else. Yeah. This is also the same. This is a bit more complicated. The idea is that I have a shallow handler that goes from C to D. It's going to turn into a deep handler that goes from C to a pair of things. I don't know why I decided to write products that way, but where either it can give you back a C or it can give you back a D. So the idea is we can either choose to properly handle it or to basically forward it to get handled later. That's what the two components here describe. Not sure how much it's worth going into the details of that. But I guess you can see roughly what's going on in the pair that gets returned here. On this side, we're taking the operation and we're just reperforming it. And then the other component of the pair actually handles it. And then when you come to actually handle something, why do we actually throw away this part and we just handle it? Where do we use the F? The F is used in the resumption, which is exactly what you'd expect, because you want to only handle it once, and for the resumption, you just want to reinvoke the effect to be handled by someone else. So that's exactly what's happening there. It gets the pair out and it invokes the F part. Right. And I should mention sheep handlers. So this was probably a terrible name, but Stephen Dolan is to blame for this. He said, well, it's somewhere between shallow and deep, so sheep. And this is actually, in some settings, this is what you really want. And this is what we have in our extension to WebAssembly. It uses sheep handlers. And they're a bit like actually a bit like a form of parameterized handlers, but the parameter is a special thing. The parameter is actually the new handler. So basically, every time you resume, you get to choose explicitly which handler you want to insert. And you can see that here. We don't handle with the big H we had there. We handle with the H, an H that gets passed in at runtime. So it's like a shallow handler in that the body of the resumption doesn't need to invoke the same handler, but it's like a deep handler in that the body of the resumption must invoke some handler. The shallow handlers are a little bit weird because they can just be dangling, unhandled effects that just happen to get handled by something that is in the dynamic scope that you run the handler in. Whereas this is slightly more hygienic, I guess would be the word. Okay, I'm going to finish up with one last example. And we have like 3 minutes. And this kind of leads on to questions about how effect typing works. So here we're going to compose two different effects together. One of them is a reader effect. It just has a get operation that reads natural numbers. The other one is an exception. We'll call it fail. And the idea is we're going to implement the reader by passing in a list of natural numbers, and each time you read, you'll get the next one in the list. But if you run out, then we're going to fail because we've run out. So here's this reads handler. If it's an empty list and you try to read, then you get a fail. Otherwise, you get the value you expect, the n there, and you continue. So this is a parameterized handler. And then we have an exception handler that just handles failure as nothing. So we've seen this before. Yeah?
You've got a type fail for eight. It doesn't mention fail.
This is true. Yeah, there should be a fail over here. Yes, and this is actually the key point. So thanks, Philip. And
Failing a fail is one.
yeah. And you might hope that, well, I can compose these two things together and I end up with some kind of function that takes in a reader computation and gives me back a pure computation. Because we're interpreting the failure in as a value. But that's not what happens. Yeah, maybe this is a bit subtle to be doing right at the end, and I'll probably have to come back to this. Yeah, so I can compose these handlers together like this, and I get something that has the right type, but does it do the right thing? So here we're sort of moving on to thinking about effect polymorphism. So supposing the computation I want to handle, it's going to read something and then add it to, raise an exception. But the reads handler I had, that doesn't do anything with fail. And the idea of encapsulating this effect is, well, I want the failures here to get turned into something that's pure. But that's not what happens here. What actually happens is it handles that fail as nothing. The thing we would actually want to happen here is this fail should be treated differently to the one that was an internal implementation detail of the things we composed. So what we're really trying to do is to have something of this type. You see the subtlety. We don't want to be handling failure here. And what I actually want to get out if we ran that example, then we should not get something pure out. We should get something out that actually raises an exception, and then you should handle that exception further up. And yeah, gone over, and I'm going to stop, but I'll maybe talk more about that next time.